So, good afternoon, everyone. We are almost finishing the conference, so I'll try to be quick, but I will share some of the main ideas that I have in this field that has been changing so much lately: semantic search, speech recognition, summarization. I have to tell you as a preliminary note that I have a lot of articles published in Towards Data Science and Medium regarding this topic. So if you want to get a more in-depth version, go for it. In this case, I'll have very clean slides for this presentation because I want to focus really on concepts and ideas. So if you want more in-depth references, please go to those resources. So I could call the talk Random Experiments with Large Models in the NLP Space, because it is kind of the journey that I did while building features into new products or existing products using some of these technologies. So I will share a little bit the journey and what I find interesting versus what didn't actually work. So let's start with the basics. So we all know the ChatGPT wrapper, right? And this is what we have so far here. So let's start with that and just get a sense of how can we basically integrate all these new technologies and tools together. So this is as easy as it can get, right? We have an input system that we want to source some data from. In this case, let's say I want to get my releases from the Spotify API or something like that. It is a large corpus of text. So I could manage everything by myself and then use some kind of OpenAI API, for example, and do all the processing myself. Another option is to use some middleware. Today you have LangChain, you have a ton of tools in that space. Now the interesting thing is that for simple tasks, it works quite well. For example, in this case, you have a large corpus of data, so you cannot really summarize everything because we all know there's token limits for most of the models. And so one thing that LangChain, for example, offers is a way for you to what they do a map reduce. So you map a bunch, and create a bunch of chunks from that large corpus, you get some, and you use a specific prompt for that, you get a bunch of summaries from those chunks, then you concatenate everything, and that is the reduced portion, you then get a summary of summaries. Obviously the accuracy decreases with that approach, but you can also define a specific prompt for the combination. So for simple tasks like this, you can use an approach that uses existing tools and kind of the overhead is very small. Now, another concept that I need to introduce here is semantic search. Probably a lot of us have worked with it. So the semantic search is basically the activity of retrieving documents, right, based on their meaning rather than any other aspect. For example, keyword search. Keyword search have been around for a long time. Now we want to really focus on the semantics, as we saw from the previous presentation. Now the idea from semantic search is that you'll have a corpus of documentation once again, and what you do, you have to somehow encode this information in a numerical structure. We do this by using embeddings, and we can use embeddings like, for example, some model to produce those embeddings like the sentence transformers, as it was also pointed out in one of the talks. And the basic idea from semantic search is we want to compute distances in a high-dimensional space, but just to simplify, let's put it in a 2D space. So we have two vectors. Let's say that the green vector is the query vector. So what the user is actually querying at that point. Like the question, is francesinha a dish from Porto? And what we do is we will get from our documentation a kind of the closest vector that we can find. And the closest here means some distance measure. We could compute the L2 distance, we could compute cosine similarity, or any distance metric. So now that we understand semantic search, let's move to how can we do this at scale. And I'll be quick here. The idea is, so I will just focus on cluster-based methods, but there are a ton of them, graph-based methods, there are a ton of ways to do this. But the main idea, for example, with index partitioning is, well, let's cluster our vectors. So the vectors that we just saw previously are represented inside of those structures that you see there. And those structures are actually clusters. And we compute the centroids for each cluster. And then what we do is we compute the distance between the query vector and every centroid that we have. And as we find the closest centroid, then we go into that cluster and we compute the distance between the query vector and all the vectors inside that cluster. So we see that we have much, much less computations. Another thing that we can do, and we can actually do both together, is product quantization. So how does product quantization work so let's pick up this green vector that you see in the picture, right? We are basically cutting through or creating slices of that vector like we call subvectors, and we are clustering those subvectors. And so we have several subvectors that will belong to the same cluster. We compute the centroid, and what we store in the final vector is just the centroid that we got from those clustering. So the representation, as you can imagine, the dimensionality of the problem reduces very much. Now, we know about semantic search, but to do semantic search at scale, it means for us, like from the software development community, it means using databases, right? And the thing is about databases is the data structure of vectors is not really something that we are used to work, at least in the past. Now we have a ton of vector databases. But the main idea we already know. We have the data, we have the embedding model, could be sentence transformers, we create the vector embeddings, we store the vector embeddings. Now, how does the process work after that? So we have an application, the application will have a query coming in from the user, we run it through the same embedding model, we create a vector representing the query, and then we just hit the database with that vector and compute the similarity measures using any technique that we saw. Pretty simple, and we return kind of the top 10 results to the UI, for example. Now, one question that I often get is, what is the difference between a vector index and the vector database? Now, a vector database, we already know what it is, and it's like the database concept is pretty well known. We can replicate the data, we can scale it, we can have real-time updates, all of these things. The most relevant feature in like that differentiate both of them is also that we can store metadata with the vectors themselves with the database. That means that we can filter out a lot of the information just from the metadata that we store. And there's a bunch of them. There's ChromaDB, there's, if you go for serverless, there's Pinecode. Postgres now supports vector structures as well. Now, the vector index is kind of the lightweight representation of that. So what you can do with the vector index is you have to perform everything in memory. So you'll have to have memory to actually spare for it. But since everything is in memory, it's very easy to set up, very simple to set up. It's fast enough. Now, the question that I got wrong while developing it was, like, if you have a lot of writings to your system, if there is a lot of new documents coming in, please don't use a vector index, because you have to reindex everything every time. So if you have a lot of writing, you should go for a vector database. Now, moving on to a different concept, and I told you there's a lot of kind of different aspects come into play in this talk. Now we go to speech recognition. So one thing that I was very interested in with speech recognition is obviously we want to do automatic speech recognition. We have an audio clip and we receive that as input, and we want to transcribe it accurately to a text representation. So probably one of the state of the art right now is Whisper. That was open sourced by OpenAI recently, and it's a sequence-to-sequence transformer. Now, the interesting thing is that it can perform different tasks. It can transcribe, it can translate, and multi-language, it supports multi-language. You can translate from several languages to English. And just quickly overview of how it works. We have a conversion of the input audio into a 30-second clip, which is converted then to this log-mel spectrogram. It's a representation of the audio that we input to the transformers. It's a sequence-to-sequence, so we have a encoder, we have a decoder, and obviously we have to have the positional encodings because it's sequential data. We are working with audio. Now, the interesting thing, look at the tokens now. So in terms of the tokens, you have the start token, then you have the language, then you have the task, and then you have the timestamp, and only then comes the actual text. So everything is passed during the tokenization process. And as with any model, we then have we are predicting the next token, right? What we do also in the LLMs. Now, some limitations, and I'll go quick on this. So one of the limitations is resources with Whisper, because it's pretty slow. It's not super resource intensive in what you need, for example, in terms of VRAM. If you use the larger model, there it comes in different sizes. You need around 10 gigabytes of VRAM. And with GPU, a 30-minute audio clip will take you around 15 minutes to transcribe. Fairly slow. Another problem and another limitation is I wanted to do speaker diarization, and I needed word level timestamp. So I needed to know exactly when a word started and when a word ended. And Whisper is not good at that. Now, enter WhisperX. So WhisperX is a version of Whisper, so it uses Whisper to some extent. The difference is that the input audio signal that comes in, what we do first is we use a voice activation model. And this detects the speech and detects the silences. So if we have parts of our audio clip which are just silences, we can just trim them down because we don't need them. We will not transcribe anything from that. So we are saving ourselves some space. Then we have the cut and merge algorithm. Now, with Whisper, you are basically cut randomly 30-second clips. The problem with that is that if I'm speaking right now and I don't stop, and the 30-second window comes in and I don't stop talking, like the boundaries where the cut happens will degrade performance. With this approach, you will not have that. Now, the third thing is the authors propose that we assume that the segments are conditional independent. And that means that we can batch them together and we can parallelize everything. So it is much, much faster. Like the last piece of information which is useful for us is the phoneme model. So the phonemes are the shortest units of speech. So if I say tap, p is a unit of speech. And the idea is to understand where those things happen and where does the words happen, and connect both, basically. So you get accurate transcription, but also word-level timestamps. Now, moving on to a different concept, function calling. Most of you have probably heard of this. It's a feature of a lot of large language models. Now, the interesting thing for me that I was thinking about is this could really revolutionize the way we build data pipelines. Because data pipelines, they run once in a while, they are pretty static, they are requiring heavy engineering effort. And the way function calling works is you set basically a list of functions, right? I have a list of functions that I define with the name, the description, and some parameters. Now, let's say that a prompt comes in and the user says, send an email to Luís to pay his subscription. Now, what the large language model has to do is basically understand which functions it has available. And if it has available one function that is get email, and the parameter is a query, so the LLM can write SQL. So let's inject that SQL in as a parameter to the function. Now, it has another function that is send an email that calls kind of an API of a service, Python service that just sends out notifications. So, and you have to write the body of the email with HTML, for example. Well, the LLM knows how to do that. It can do that, it can call that endpoint, and basically an email will be triggered. And so you can see that it's very dynamic. Obviously, there's a lot of safeguards that need to be in place. Now, we've talked about a lot of chaining of things, right? There's some reasoning happening, chaining of stuff. Now, this calls out the concept of agents. Agents are basically LLMs that can do different tasks, chain different tasks together. Maybe it's Q&A, maybe it's reasoning about something, maybe it's processing something. The interesting thing is on the left, we already know, on the right, actually, we already know everything, right? You don't have to worry about that. We know about vector databases. Now, what interests me is one concept, for example, is have some sort of external memory to an LLM, right? Because if we go to an LLM and say, what is Falcon 40B and can I use it commercially? we will get the answer as a large language model. I have no idea what is Falcon 4TB. Now, if we have an external memory, like a vector database, and we can use semantic search to grab interesting documents to share with LLM in that specific timeline, then it can actually answer us. But more than that, we can actually get some of the important and more relevant sources. And since we are computing a distance measure, we can also attach a score. Let's say the first reference has an importance of 90% to what is being answered in this case by the LLM. Now, I promise this will be kind of the last concept and idea. Obviously, everyone heard about fine-tuning, right? And the thing here in terms of fine-tuning is, I've put it together, or inside, let's say, transfer learning. And you have supervised fine-tuning inside of fine-tuning, because you can do fine-tuning with reinforcement learning, for example. But with supervised fine-tuning, you have two main constraints here. Is data, because you don't have 1 trillion tokens to teach your LLM to be better at coding in Python. Maybe you do if you are Stack Overflow or something like that, but usually you will not have that amount of data. The second thing is resources, hardware. We're not OpenAI, Google, Meta, so we need to be very conscious about resources. So there are two techniques that I want to share here today. One is LoRa. So LoRa, low rank adaptation. So what we do with this low rank adaptation technique is, basically I'll try to explain in a simpler way. So what we have is a matrix W. These are our weights, right? This is a 1,000 per 1,000 matrix. And this is usually full rank, so it's very expressive, this matrix. Now, the thing is, we want to tweak it a little bit, but not too much, because we cannot really retrain our model. So to tweak it a little bit, we will need, again, in this case, we are adding a matrix that is the same size, so the same shape. And we get the W prime, which is kind of our fine-tuned weights. Now, the way we get DW is the interesting part. So we pick up two matrices which have lower ranks, so matrix A and B, so they have less information. And by matrix multiplication, we will build a matrix 1,000 per 1,000, but this matrix is much less expressive than W. But what has been shown is that we get enough explainability to actually get our LLM to perform better with a specific task at hand. And so the quantization LoRa is, we talked about quantization. So the quantization part of this low rank adaptation is basically just reducing the memory requirements for the weights of our model. So usually we have full precision. If you pick up any pre-trained model, you have full precision. Means that we are storing the weights with 32 bits. But we could use half precision, 16 bits. And what happens is that it will degrade accuracy a little bit. But what I can tell you and what is being shown is much better to use larger models with lower precision than the reverse. You get much, much better results. And today, you can actually do 4-bit and 8-bit precision these days very, very easily. And this is just a result of a fine-tuning exercise that we did. So a 4-bit Q-LoRa of the 7B Llama 2. So this is the smallest version of Llama 2. And you can see here the prompt that we asked the model before and after the fine-tuning. And what you can see here when we ask, write a function that reverse a linked list. So this cannot be more basic than this. Now, if you look at the base model, it goes and asks again the question, or writes the question again, write a function that reverses the linked list. The Python code is not organized, not syntactically correct, nor logical. And then it goes and it starts to hallucinate. It continues to go with write a function that counts the number of nodes in the linked list. So it has nothing to do with what we asked. After the fine-tuning, you get a much comprehensive answer. You get, here's an example implementation of a function that reverses a linked list in Python. Notice the organization of the code. It creates classes. A node creates a linked list. There's some logic problems still in the code, but remember, we are using the smallest model possible. And you see, it goes to explain. what he did. In this implementation, we define a node class, represents a node in the linked list, and it goes on. So it is already available for us, capabilities for us to fine-tune the large language models towards our specific use cases. So that is already available with consumer hardware. And that's it for me. Thank you.
Well, thank you so much for this masterclass on LLMs and all the concepts around. So it was great to listen to you. So we have a lot of questions. Let me start by the first one and most voted. From your experience using WhisperX and cutting the original audio in chunks, some people are saying that they get less context, and especially with Portuguese audio. What is your experience on that?
That is true, but at the same time, you have to do the same with Whisper. So you cannot really process longer sections of audio clips. So the way WhisperX does that, as I explained, is it tries to minimize any kind of silences, but any problems that might appear in the boundaries of your audio clips. Now, when it comes to Portuguese, for example, it is basically the Whisper that is probably the potential problem here. So when OpenAI trained the model and open sourced the weights, it probably didn't have so much Portuguese information. So that's kind of a constraint of the model. With WhisperX, that is not affected at all. So I wouldn't expect any deterioration of accuracy because you are using WhisperX for that purpose.
Okay, good. Another interesting question, I also had this one. As you talked about LangChain and all the orchestration and workflows that we can define today with agents and everything. And the issue is about observability on this. How do you see this challenge when defining very complex workflows, calling APIs, functions?
Yeah, that's a very, very interesting question, because the problem that arrives, for example, I talked about data pipelines, and that's why I said that we need a lot of safeguards in place, is because obviously every kind of answer and process that we follow from the LLM perspective has some stochasticity in it, right? It's not deterministic. So, and we are used to deterministic approaches for pipelines. Now, the thing is, we can try to reduce that, and I would say it's like when you develop a system that has, I don't know, microservices, there's inconsistencies in the data because you have to manage kind of the communication between systems, and it gets a little bit more complex. And I would say the same thing applies here. So you need safeguards, you need functions very well defined, and you need kind of ground rules for what can happen, what are the boundaries that the large language model can go in terms of reasoning, in terms of using certain functions in conjunction with others. So there are certain rules that will reduce somehow the search space. In terms of guardrails, it is the same if you think about how OpenAI and the rest of the big players in the market need to guardrail somehow like aggressive content in the way a large language model works.
So we are evolving from microservices architecture, SOA from the past, and this new approach. Okay, another question. How do you decide between performance degradation and cost speed when using LLM?
Yeah, that's also a good point. So what I said is I would always go for bigger models if possible, and I'll try to reduce memory, for example, constraints through quantization. It has been proven that it is much, much more efficient. So that is one of the things that can be done. Then it's about like what techniques are we using, for example, to fine-tune these models. And when we need to do that, and we can use LoRa or any other techniques, is really about trading off, obviously, some accuracy with some costs that are kind of overhead that we have computationally. But I think that is kind of the hard part of it. We have to find out if it answers what we are expecting in terms of the output of the model, test it very well, test different data sets, different evaluation metrics. So the pipeline to evaluate these models needs to be very, very well defined.
Last question from me. If you're looking at all these concepts from prompt engineering, function calling, plugins, embeddings, vector databases, orchestration, how do you see in the future? What are if I'm a data scientist, what are the areas that I should invest studying?
Yeah, that's a hard question. I think obviously there's a lot of noise around like prompt engineering and all of these things. I think they are somehow important to certain aspects because it impacts kind of the output that we get from the model, but they are limited in knowledge required, right? They are pretty common sense, or you have certain aspects that you learn through doing it, but it's not something that I would say, let's focus on that. I would focus definitely on getting our hands dirty on how to fine tune these models, how to leverage these new approaches, because my perspective on the future of how this will evolve is we will have certain very large models that are used as kind of for a broader range of topics for generic tasks. But most of it, we will have very local and specific trained models that are very, very good at specific things. And my 2 cents on that is if a company in the future wants to do customer service and automate it completely, I don't think that it will rely on some generic large model. It will have to rely on their own data somehow and fine-tune it somehow, at least a portion of it. So if you have the understanding of how things work on the back, you will be much, much better well-positioned for everything that comes right after that.
But do you see fine-tuning as a better approach than, for instance, a RAG, the pattern that we are seeing now?
I think, again, I think everything will change during this time, right? Everything will evolve during this time. And I think a lot of different techniques will come. I think the most important thing is that we should sit closer to everything that has to do with preparing the models for specific use cases. I will put like that, to specific use cases. In terms of like plugins and all of these things, they are interesting, like integrating all these systems, but they are more interesting in my perspective to OpenAI, for example, than the rest of us. Now, function calling could actually be something that is very interesting. So improving that feature on local trained models with our own data could really change the way we operate data pipelines in the future.